Hi guys, welcome back to my channel. Today we're going to do a physics passage. You're welcome to take a screenshot and give it a try on your own before we dive into this. We're first going to read the passage and do all three questions, right? So let's dive into this. So the passage reads, rigid plastic tubing is used in various medical devices and applications. Researchers designed a flow sense to measure the flow rate of fluid inside of plastic tubing. Okay, so I know that this setup is to measure the flow rate of fluid, right? So flow rate must be a big theme of this passage. All right, let's keep reading. Flow was detected through a contactless technique whereby an excitation electrode and one or more pickup electrodes are placed in close proximity to the tubing. The application of AC voltage causes AC current to flow through the fluid. At other locations, the electrodes are in contact with the tubing and act as capacitors. Figure 1 shows a diagram of the flow sensor. Okay, so figure 1 is a very nice schematic summary of the paragraph, right? This is what a flow sensor looks like. We see the AC source that was mentioned in the paragraph and all the electrodes, right? Okay, perfect. Let's keep reading. Okay. So figure 2 depicts an equivalent circuit modeling electron flow through the tubing system in figure 1. CX1 to CX5 are the capacitances formed at the 5 electrodes. Okay, so if I look at my figure 2, I see that this is a CX1 to CX5, right? CX1, CX2, CX3, CX4 to CX5. Okay. And then RX1 to RX4 are these, right? RX1, 2, 3, 4. Okay, they are the equivalent resistances of the fluid sections between adjacent electrodes, okay? And UX1 and UX2 are the two voltages measured in order to deduce the fluid flow. And then UX1 equals V1 minus V2. VX2 equals V2 minus V3. No current flows through the voltmeters in figure 2. Okay, so very nice, right? That's figure 2 in the context of a circuit where there's an electron movement, right? So this is really analogous to figure 1, but the difference is figure 1, we really have this application of fluid that's flowing through this plastic tubing, right? Okay, let's keep reading. By determining the time delayed T between the measured voltage UX1 and UX2, as those voltages vary with time, the researchers can determine the flow speed. Okay, if L is the distance between the centers of the two sections measured by UX1 and UX2, the flow speed V is given by. Okay, so this is a flow speed. Okay, so this is flow speed. This is flow speed. And then it's L over, this is basically the time delay T, right? Because we said that we're using this time delay T and also L to measure the flow speed. That's what the paragraph tells us. So even if, the symbol looks a little different, but you can really infer that from the passage, right? Okay. So let's read the legend for this equation 1. So equation 1's measured voltage UX1 and UX2 for, no, that's not the legend for equation 1. Okay, I thought that's going to further explain equation 1, but it's talking about the figure 3. So, okay, so that's all about this equation that we have. Okay, so usually the given equation will be tested. Okay, so we really want to know all the variables in this equation. Okay, V is the, once again, flow speed, right? Is the flow speed, okay? And then L is the distance between the centers of the two sections measured by UX1 and UX2. And then if you look at this picture, figure 1, then you can see this is L, right? It's the distance between UX1 and UX2, okay? That meets the paragraph wording. Okay, now we can keep reading. So measured voltages of UX1 and UX2 for one trial are shown in figure 3. Okay, so that we know figure 3 is basically measured voltages, right? And then also remember UX1 equals what? Equals, there we go, V1 minus V2. VX2 is V2 minus V3, okay? Okay, so those relations that in the passage are most likely to be tested. So we want to be sensitive about those, okay? All right, let's keep reading. Okay, the distance L, okay, perfect. Distance L is a 20 milliliter, okay? So if I were to calculate flow speed, I know L is a 20 millimeter equals to 20 times 10 to the negative 3 meter, right? Okay, and the inner diameter of the plastic tubing was a 3.9 millimeter, okay? Diameter 3.9, okay. So now this is figure 3, okay? And then figure 3 says, yeah, it's a voltage, right? Basically, it's the electric potential, right? And then that's what causes the electrons to flow, right? Okay. So voltage traces from sensors UX1 and UX2 labeled U1 and U2, okay? So this is UX1, this is UX2, right? And then once again, UX1 is V1 minus V2, this is V2 minus V3, right? Okay, all right, so that's it, right? And then also we notice that we see this symbol here that really looks like this, right? It really is the time delay t. So if a question asks about the flow speed v, then we can really calculate it if we can tell what is exactly is this the time delay t. Okay, all right, let's jump into the question. This is an overwhelming passage. There's a lot of information, intimidating figures, right? But it's okay. I mean, I know my relationships, right? I know you know what does everything stand for. I know all the variables, and then I think I'm good to go. Okay, so first question says, based on figure 3, okay, figure 3 is here, okay, based on figure 3, what is the approximate flow speed? Okay, so it's asking about v, right? So according to the passage, v equals what? L over this t, okay? So L, we know that it's 20 times 10 to the negative 3 meter, right? As you know, we're told here, okay, 20 millimeter, okay? And then the t is really what? Is really this much, right? This much is this t. Okay, I just need to figure out how much is this much, right? So I know that going from 0.4 to 0.5, right? Going from 0.4 to 0.5, that's about 0.1 second, right? Because 0.5 minus 0.4 gives me 0.1 second, okay? So it's really 0.1 second. And then I would say like this is about the half of that 0.1 second, right? So I would say like going from here to here, it will be 0.45, right? And then going from here to here, it will be a little bit less than, you know, half of a 0.1, which is a 0.5 second. So I would say this is a 0.4 second-ish, okay? Or I can even use this. I mean, there's really not too much difference, right? And then if I plug in the number, my L is this much meter minus 0.04 second, and then that gives me 5 meter per second. Okay, all right. So that is the calculation that you need to do for this, right? Really simple and easy. I mean, this passage looks really intimidating and overwhelming, but like I said, equations that given are usually tested. So you really want to know, okay, in this equation, what is measured? That's the flow speed v, right? And then it's a L over t. Then you want to find in the passage where is L, and then where's t. And very nicely, this question is based on figure 3. So it basically tells you to look at figure 3 for this time delay t, right? Okay, perfect. So that's this first question. Let's move on to the second one. Second one is challenging, okay? It says, what direction of flow can be deduced from figure 3 given the setup indicated in figure 1, okay? So the setup in figure 1, what is flowing in figure 1, right? In figure 1, it's this current, AC current, right? It flows through the fluid. So it's really the current that's flowing through the fluid. So it's current plus fluid, whatever you want to say this, but right? But I know that that's what's flowing in figure 1, right? Okay, the reason we want to know what is flowing in figure 1 is because really the electron flowing direction is opposite than the current flowing direction, okay? It's another, I need to make another video to explain the reason, but this is a background knowledge that you know, okay? So you want to know what is flowing in figure 1. Okay, it is current, okay? All right, and then we have to use the information from figure 3 to tell how is the current flowing, right? To the left or to the right, or first to the left, then to the right, or D, right? So that's what we want to know, okay? So from figure 3, we see that, okay, if you noticed that UX1, right? UX1 starts from 2.6, right? And go all the way to 2.75. But U2 is really what? U2 is really starting from 2.35 and go all the way up, maximum 2.5. So U2 is always lower than U1, right? Which means what? Which means V1 minus V2 is always larger, always larger. It started from a larger number, you know? It's always larger than V2 minus V3, right? What does that tell us? V1 larger than V2, larger than V3, right? That's what it tells us, because V1 minus V2 equals U1, and all of U1 are positive numbers, so you must know that V1 is larger than V2, and then V2 larger than V3, so that gives you this relation, right? So if V1 is larger than V2, larger than V3, as you can see here, V1 larger V2 over V3. I mean, this setup is electron moving, but this is figure 1 is a current moving, right? Also V1, V2, V3 here. And then how does current move? Current moves from higher potential to lower potential, okay? So that is the flow, okay? If V1 smaller than V2, larger than V3, you know, then it will have all left to right and first left, first right, first right, first left, you know, those situations. But this is all the way through, like going to the right, from the higher electric potential, aka higher voltage to lower voltage. That's the rule how the current flows, right? That's not the rule for electron flow, because the electron flow has the opposite direction than the current flow. But the figure 1, the setup is AC current, right? Flow through the fluid. So that to answer this question, what direction of flow can be deduced from figure 3 given a setup indicated in figure 1, it will be to the right, right? All the way to the right. Okay, the last one. Suppose the same tube used in experiment depicted in figure 3 were used in conditions where the flow speed was 0.1 meter per second. What volume of liquid would flow past each electrode per second? Oh my gosh, this is really challenging. It's wordy, right? And then at this point, your brain is tired. So, okay. It's okay. We get this, okay? So we get what? We get V. V equals 0.1 meter per second. That's what the question stem tells us, right? And then now it's asking what volume of fluid would flow past each electrode per second, okay? Volume per second, okay? So if you look at this volume per second, you will realize this is what? This is flow rate, right? This is flow rate. So if I were to draw a picture for you. Okay, I'll just draw it. So basically, this volume per second is say, okay, this is 1 second, right? 1 second. So 1 second, how much stuff like go through? What is the volume go through this tube in 1 second, right? So this is basically what? This is basically Q, right? This is basically a flow rate, right? Okay, and then you can see that if this is a cross-section area and then this is the D, or distance, okay, then V is really A times D, right, over S. And then this D over S is really what? Really V, right? So it's really like AV. And that would remind you of the continuity equation that A1 V1 equals A2 V2, right? We say the flow rate is constant all the way through, okay? So now we already know the 0.1 meter per second is the V. We just need to know what is A so that we can calculate Q, right? All right, so what is A? A is the cross-section area, right? And then it's really this a circular shape, right? It's like, so what is the area of a circle, if you will, right? If it's a pi r squared, right? And then what is R? R is we don't know R, but we know diameter is 3.9, I say 4 millimeter. So the R is really what, 2 millimeter, right? Okay, so if we were to write it out, let's write it out. Okay. Oh, okay, I'll just put it here. Okay, we're gonna write it out, okay? So we'll use a different color. So Q equals pi, R is really 2 millimeter times 10 to the negative 3 meter, right? Okay, squared, okay, squared, and then times what? Times V, which is 0.1, okay, 0.1. And then I'll just round it to 3, okay? That's 3 times 2 to the, this, and times 1, okay? So that will give me the final answer of 10 to the negative meter cubed, okay? So that will be my final answer. But as you see, the choices, they are what? They're in centimeters, right? So you go from meter cubed to centimeter cubed, you will times 10 to the 6, right? So after you time this to the 6, that will give you what? A. Okay, so that is the answer. So this is a really challenging physics passage, but if you have you put the hard work and then you just go over this over and over, and I believe this will become intuitive for you. And then next time when you see this kind of scary passage, you won't be fixated on the wording on the paragraph, but more so you want to focus on all those relationships, right? For example, let me highlight them in purple, like this relationship that you want to notice, and a very important equation 1, right? And then also you want to find the variables in the equation that's given, right? And then also the questions itself can guide you. For example, based on figure 3, then you know, oh, figure 3 here, this is tells me that the time delay t, okay? So I hope that's helpful.